I created a stress testing device that can do both tensile and bending. I could use this to stress test many different things, but my main focus was to be able to strength test the plastic welds of my previous videos in comparison to other adhesion methods. Let's pull straight into this project. The primary purpose for this product is to be able to apply tensile and bending stress on parts to help determine safe loadings. It would be nice if the device could operate on a basic desk, since that is my ideal scenario and most people would have a desk or counter. I will be building this device in my apartment. It would be nice if it was mostly 3D printed. Lastly, the lower cost of the product, the more people who could potentially be able to create their own. Like it was said in the requirements and objectives, the device would need to be used on a desk in my apartment. Let's look at some options. I would normally say concepts, but all the COTS options that I could find were basically the same concept, just with different capabilities. I'm sure the most obvious answer for many is a product from Instron, or even Test Resources. These products have a complete suite for tensile testing that makes the stress strain curves a breeze. However, these devices are prohibitively expensive. I found some old lowest end Instrons for sale on eBay for around $2,500. And all of these professional manufacturers like Instron and Test Resources require that a quote be requested. This to me says that the product is definitely not going to be a few $100s, so clicking that request a quote button is far too rich for my blood. These devices are only really intended for tensile testing, but with some likelihood of making a custom tool to make bending happen. Amazon has some options that range anywhere from $60 to $5,000. The $5,000 option falls into Concept 1, but there are a couple $60 to $700 options. However, these options are only restricted to about 110 pounds of force, which I feel really isn't enough for what I'm thinking. I would really like to see a rating of at least 500 pounds. Many of these options are just frames as well, so I'd end up having to buy all the missing pieces in order to conduct my experiment. I think I could make a similar frame that has a greater length and load rating. I was able to find one maker option that was intended to be 3D printed. However, that one is far from finished, and it looked like it was going to be intended for maybe 100 pounds of force, but not likely. It looks like I'm going to take some notes from these options and create something of the same concept, but customized to my liking. Let's get designing. First off, I would like to draw a general FBD, or full body diagram, of what general forces I think will be involved in this device. I want to be able to rate this device to 500 pounds, but I want to be sure that it will not fail at that load, so I will multiply 500 pounds by 2.2 to get 1100 pounds. This builds in a factor of safety that will help accommodate for any loading we cannot predict and ensures that the device will not fail under intended use cases. The 1100 pounds is our design load. This load will help me show you how I reason what relative dimensions may work before doing a structural analysis. In this case, it is very straightforward. We will be pulling on an object from one side, so there must be reaction forces on either side of the device. The left side of the device, where the object is anchored, will experience just about all the force that the object will. The right side will be pushed towards the object while we're pulling on it as it reacts to the force from the tension developed. We're essentially creating a bad C-clamp. We'll just have gravity pulling downward on the desk, so there isn't much to worry about there. Now we can move on to some sketching. This is where you hear about those stupid stories where someone suddenly had an idea and wrote it down on a napkin, or some other medium attempting to make a more fantastical story. I have to admit, I did go through a lot of the design process with a focus on making this device as 3D printable as possible. I completed the design of the biggest 3D printable parts and found that it was just not financially practical or timely. It would have ended up taking about a month to print with the printers I have and more than 13.5 kilograms of filament. Maybe one day I'll finish this version when I have far more 3D printers and extra filament to spare. For now, I will focus on using aluminum for most of the structural components. My first step was to gather a list of materials that I had on hand, or could have delivered in a day or two, to create the project. I had 20 5/16 aluminum rods and coupling nuts, a 12 by 12 3/8 inch thick 6061 T65 plate, and 50 flange nuts being delivered by Amazon in the next day. I did also already have all the hardware I was going to use in the 3D printed version of the project, and a bunch of stuff I've had for a while. Knowing this, I can start thinking about some required features and how they would basically look. I knew I would definitely need supports for the aluminum rods so that they wouldn't buckle under the load, which would be very likely to happen with a 30-inch span with couplings. I decided the best place to put them would be on the coupling nuts. The second most apparent feature would be a brace that would slide along the aluminum rods acting as a rail to prevent rotation when applying tension. Now that I have the basic idea, I can move on to some more detail. Since I know the length of the aluminum rods and the coupling nuts, I know what the length of the threading I will have to create in the rods. I can get the rough idea of what the rod supports will look like, as well as basic features for the brace. From there, I can move on to CAD. An important mindset to have when designing something is how it will be manufactured. A large number of engineers significantly lack knowledge on manufacturing, and this results in products that are either very expensive, end up being highly altered from the original design, or completely thrown out and redesigned. While designing these parts, I want to think about the capabilities of 3D printing and the tools I can use in my apartment. So when I'm thinking about thicknesses, lengths, and various features, I need to keep manufacturing in mind in order to avoid rework. After putting a little thought into it, I would really have to make two slightly different designs if I were to make this out of 3D printed PETG versus metal structure. Even 6061, with no temper, has a yield strength that is nearly 5 times higher than PETG, so the required thicknesses are going to be dramatically different. Also, using hand tools on even something like 3/8 inch or 10mm thick aluminum would be quite the workout, so I will try to avoid going thicker than that. Here's the result. The most interesting part that I feel like the general population may not know of is the thrust bearing. This piece is a washer made of a composite of 863 iron copper with PTFE. This creates a washer that has a very low coefficient of friction, meaning it is slippery. Touching it feels like it has a layer of oil on it, but leaves no residue on the fingers. It's actually quite amazing. I used it between the coupling nut and the aluminum plate so that the contact between the two doesn't create a huge amount of friction, and even prevent the steel coupling nut from cutting into the aluminum. I put a washer in between the bearing and the coupling nut to help distribute the load over a larger area. I decided to include a swivel somewhere in the stack up in case whatever this device is pulling on starts to twist. The swivel will allow the twisting to happen without letting the torque transfer to the device. I changed up the brace a little to only connect to 2 rails. I didn't see any benefit from connecting to all 4 rails in this scenario. I also took out the flange nut in between the hoist ring and the brace. It didn't seem needed as the hoist ring is threaded itself. However, having a flange nut there to even further help prevent rotation may have been the most conservative thing to do. I included flange nuts at the ends of the aluminum rods to help prevent anything from loosening up. In the final build, I ended up using nylon lock nuts on the outer threads as well. Now let's run some analysis to see if we're ready to build. By far the biggest concern I'm going to have in this case are the aluminum rods. One of them can take the compressive stress of the entire design load with some good margin. However, we have to consider how long the rods are. When there is a large difference in the diameter and length of a structural member in compression, we have to consider buckling. Hence why I added the bracing at the coupling nuts. We have 5/16 diameter rods that are unsupported for about 10 inches of length. For this, we can turn to page 282 in Machinery's Handbook version 31 and follow the instructions in the Euler formula section. Speaking of the Machinery's Handbook, I just thought I'd mention that if you're in college for mechanical or structural engineering and or recently graduated and haven't received real-world training yet, you probably haven't heard of this book. If you were like me, I never had an engineering instructor that actually did projects in the real world, so they never referred to the Machinery's Handbook. I first learned of this book in high school in my welding and machining classes. This should be a book that you are very familiar with if you work in anything mechanical related. Hence the quote on the front cover, the Bible of the mechanical industries. Anyways, I'm done with my rant. Back to the math. The slenderness ratio of the aluminum rods is 64, which is lower than the example numbers in the book, but those are for structural steel. Worst case scenario, we do the calculation and find that the metal will fail from compressive stress before it buckles. We can call the rods fixed at both ends and use the first equation in the table. After running that calculation, I found that it would take about 1,848 pounds for the rod to buckle. The expected compressive load on the top two rods would be the design load of 1,100 pounds divided by 2, which equals 550 pounds. Divide 1,848 pounds by 550 pounds and you get a factor of safety of 3.36. Moving on to the flange nuts. Nuts are designed so that the rod that they are threaded onto will fail before they do, so we don't need to do a calculation here. This is a steel nut on an aluminum rod, but the thread engagement length is slightly more than a standard aluminum nut, so there shouldn't be an issue. I also won't bother doing the math to see if the nuts would shear through the 3/8 thick aluminum plate. That would be some relatively huge amounts of force. Same goes for the bending stress generated in the end plates. If this is 1/8 inch thick plate, then I may have taken the time to do the math. This plate is supposed to be 6061 T651, which has a yield strength of 40 KSI, which is almost 10 times that of PETG's yield strength of 4.3 KSI, according to the manufacturer Overager. The PETG version needed to be 1.5 inches thick in my first go of this design, so 1/10 of that is just over 1/8 of an inch, 1/3 the thickness of the plate I have. I don't think the threaded rod acting as a lead screw will fail in tension, but I thought I would mention that when doing stress calculations for threaded rods, you can't use the nominal diameter of the threaded rod. You have to go to the Machinery's Handbook and find the tensile stress area of the threaded rod. In this case, it's on page 1978 in version 31 and states an area of 0.0524 square inches. Divide the design load, in this case 1,100 pounds, by the tensile stress area and double check the rating. In this case, I got about 21 KSI. The biggest reason I buy from McMaster-Carr for critical components are the strength ratings. This medium strength rod is rated for 125 KSI, which is 5 times higher than our loading with the safety already baked in. I was tempted to just call the bending attachment not likely to fail based on intuition alone, but that would be very irresponsible given the consequences if it failed. Knowing that the design load is 1,100 pounds, we can assume that the load will be shared between the two connection points since the load will be applied at the center of the aluminum beam. From here we can start with the simplest calculation. The aluminum beam is being pulled on, so the PETG bracket will have to resist the shear load of the beam trying to pull through it. We just need that area that would be created if the beam were to shear through the plastic. That area is going to be the thickness of the material in front of the beam, 1/2 inch, times the length of the engagement of the beam and the PETG bracket, 0.6438 inches. That number ended up being so weird because the chamfer I ended up adding in. We then get to multiply this area by 2 to account for the double shear. After calculating the expected stress, I got a factor of safety of 5. It is important to note that this is assuming that the 3D printed bracket is solid, meaning no infill. If I didn't print this solid, my shear area would be the same length of engagement, but the thickness of material would only be the thickness of the shell when slicing it for 3D printing. There unfortunately isn't an industry standard way that I know of to figure out what the shear strength would be when including the infill in the calculation. Now let's move on to the last structural concern I have. The last concern I have is the bending stress at this point. The moment is the 550 pound force times the distance from the axis of bending of 2.8815 inches, which is about 1,584.0 0.825 inch-pounds. After calculating my moment of inertia and plugging in the numbers, I get a stress of about 11.3 ksi. That is way higher than the allowable 4.3 ksi. Therefore, I'm going to have to add some significant thicknesses around this area to confidently handle the load. Alternatively, I could make this part out of even 6061 without a temper if I had the tools or funds to do so. A potentially dangerous failure was definitely averted. It looks like I'm going to have to change the bending bracket, but I unfortunately already printed the part in hopes of saving time. I will have to test the bracket in the next video since this video has already taken a long time to make. Intuition can really save a lot of rework, but analysis cannot be skipped for the times that you may be wrong. Now let's get to building. I first prepared and started the 3D printed parts so that I can work on other parts as they print. Part of the bending bracket turned out to be a support monster of a print that only like 10% failed. I needed to print it in that orientation for optimal layer strength. I then decided to start threading the aluminum rods. However, I had a heck of a time trying to clamp onto the rods so that they didn't spin during the tapping process, especially since I didn't have a vice clamp with soft jaws. I ended up creating a rod clamp. Maybe you saw the short that I made that you can print for yourself if you'd like. Now that I have moved farther along in the print queue, I was able to use the template that I printed to cut the end plates out of the 3/8 inch thick aluminum and drill the holes. This ended up being a heck of a workout since I only had a hacksaw at my disposal. I made sure to have all the edges that I cut not at the bottom edge of the end plate, and that was definitely a good call. The surface flatness of the hacksawed faces would leave a drunken blind monkey in absolute awe. Nonetheless, many of the features would still work even with the widest of tolerances, and everything came together great. The rod clamp couldn't have worked better, even after being used with 12 rods being hand threaded on both sides. Now let's get to some testing. To verify that the primary structure can handle the 500-pound load, I hooked up a chain to the scale hook and the swivel. I began to slowly apply tension to the chain and thus loading the frame. Tell you what, no matter how much math you do to verify everything will work, the nervousness does not go away when testing the design for the first time. Despite the nerves, the thrust bearing and greased rail guides and threaded rod did an amazing job at keeping the friction low, and there wasn't even a creak to be heard when applying the load. I didn't notice any deflection anywhere in the device, even at 500 pounds. It's a success. I can't wait to move on to the next video testing the strength of my plastic welding method and a couple other methods of adhering plastic. Don't forget to subscribe so that you get the soonest chance to check out the next video where I stress test some plastic welds like the ones in my videos. The STLs for this project will be on Printables, linked in the description, and later on my website whenever I can get to finishing that. Starting a YouTube channel is turning out to be a whole lot of work. Thank you for watching. Please consider liking, commenting, and subscribing. Don't forget to share this video with anyone who might be interested, and thanks for sticking around.